And in the second part, Stanley will brief you about the data labeling in deep learning and also the detector model. And as most of you, I'm also a newcomer for MATLAB. I will also wondering what is MATLAB. So from MathWorks, we can say their introduction. MATLAB is just a programming and numeric computing platform to analyze data, develop the algorithms, and create models. So basically, MATLAB is a programming platform designed specially for engineers and scientists. And the heart of MATLAB is a MATLAB programming language, which is a matrix-based language allowing the most natural expression of computational mathematics. So what can we do with MATLAB? Using MATLAB, we can analyze data, develop algorithms to solve problems, and also we can create some models and applications to solve real-life problems. And the languages, apps, and built-in math functions enable us to quickly explore multiple approaches to arrive at a solution. So MATLAB actually takes our ideas from research of production to the production by deploying various toolbox and functions. So the first one we need to start is I will show you the MATLAB interface, and we will get familiar with it. Let me share my screen. Can you see my screen? Okay, thank you. So here is the MATLAB interface. It's a basic thing we need to know. And here is our home base for coding and where all our projects begin here. And I'll give you a brief overview of their functionalities. In the middle, we will see the command window. This is a window we spend most of the time in. Here we can define the variables and manipulate them to finish a few tasks. So for example, I let s equals to from 1 to 10. And then it will display immediately on the screen. And we can say our variable is saved to the workspace, which is the right side of your interface. And the right one is called the workspace. You can say any variables you have created in this workspace. So when you double click it, it will be open in the editor tab. So this one looks very similar to Excel, right? Here you can edit your variables in a faster way. For example, let's edit A6 to be 3. And we can also do the matrix transpose. Just right click them and click the transpose variable. Okay. And also we can do the sorting to the variables. We can right click it and sort by selected columns. We change it to descending column. Yes. And on your left hand, you can see the contents and file hierarchies in the current folder here. If you click one thing, you will see the information of your file in the details window. Okay, let's write something to say what will happen. So we redefine it to be 1 to 10. Okay, then we define y to be log x. So we can say we have created two variables here. So now I'd like to plot the relationship of them. So I use plot function. Have you seen the image? Let me check. Okay, can you see the image here? Okay, so this is a basic plot function we will use. And also we can do some other general commands, like we can save the data to our computer using save command. Save my data in math format. My data 1. Okay. So you can see here is generating the data and the variables we have used here. Also, we can delete the file we just have saved. Just use delete command. And then you can see the current folder, my data 1 have been deleted. And also to make your workspace more tighter and more clean, we can use clear to clear all variables. You can see the workspace now is empty. And we can also use clear command windows CLC to clear all the command history. So here is basically the use of MATLAB interface. And now we will going to meet our first program in MATLAB. So how can we write a MATLAB program? The command window is actually great if you want to execute commands line by line. Some of you may notice that the command window is actually very similar to the shell in Python. But if you want to execute multiple commands at one time, you need to create a script or a live script. So what's the difference between the script and live script? MATLAB live script and live functions are interactive documents that combine our MATLAB codes with formatted text, equations, and also images in a single environment. But the script is just a plain code. You cannot get the feedback to say what's your output during your coding. They both have their pros and cons, actually. For example, using the script, your project is tied. Using the live script, you can see your output while coding. So let's create a new script first. Yes, well, we can see here the .mlx format. We can use text to edit it. Can you see my screen? Okay. So we use text block. Our first program. And to structure our program, we can use a comment. In MATLAB, the comment is denoted by the percent sign. You can write anything here. And you can also structure your program by using different sections like this. This is 2 different section block. So we can try to create some variables. Let's just use x from 1 to 10. S equals to 1 to 10, and then y equals to, this time we use square root x. To run this code, you can use a shortcut in your keyboard, and also you can use the tool strip here. You can click run, and let's see what will happen. After executing these blocks, we will see the outputs right here. Okay, we need to save it first. Okay, I save it as first kilogram. Okay. Let's execute it. Yes, we have created 2 variables. To see the relationship between them, we can use a plot function. So this is basically the live editor. And maybe many of you have used one or more programming language, and the basic syntax is actually similar to each other programming language. Let's give you an example for if-else statement. The if-else statement is a basic decision we will make. Here, we let the user in. We define a new variable called user in, and we request the input from the user. We can say some, did you find MATLAB Interface? And we can say, give them the instruction, yes or no. And we can say, this is string variable. And then we can use if-else statement. If user in equals to yes. You can see here, different from other program, the if-else or some other, like later we will talk about the for loops. They also end with an end command here. So don't forget to add an end to your program. Let's continue. So if user in is yes, you find MATLAB is interesting, you can display hurry. And else if this one is similar to Python. Python is elif, right? So if else if user input, they give them the n, so we display. And for the last, if they don't give us an input like y or n, they give some other inputs, we will display. Please read the instructions. Okay, seems nice. Let's run it. Oh, there's a sentence pop up in the command window. So we input y first. Oh, it displays a hurry. Okay, we run it again. No. If no. Okay. Oh, you can see this line is as execute as oh man. And if I run it again, I input don't know. Okay. He will ask us to read the instructions again. Here is basically how if-else statement works. And later we can say the loops. We just start with the for loops. For loop is something similar to what we have met before. If I define a variable starts from 1 to 10, we use colon as 2, and we can display the variable I and end. So we can execute it. Okay, there's 2 and let's delete it. Yes, here is 10 variables from 1 to 10. It will every step it will increase by 1. So we can say from 1 to 10 the display. Actually, the if-else statement and loops can do a lot of things for us, and I leave it to you to explore it. And next, we will talk about something about the plotting functions. MATLAB is powerful while used as plotting tool, and these functions are essential for anyone who wants to present data visually and more nicely, since they provide a very quick and easy way to make meaningful and interesting plots. Let's go back to our command window and we clear and cell C. Before we can make a plot, we definitely need some data to input. And I will make two simple data sets, both made of 50 random numbers, and okay, we let n equals to 50. If you don't want your command being executed immediately, you can use semicolon here. Yes, and we create y random number n1. Y2 is also random number n1. These two steps is actually we are creating two arrays which has n rows and one column. So we plot y, plot y. Can you see the image here? I think no. Now you can see, right? Here is 50 random number, and here is 50 random number with the axis being from 0 to 50. And if we plot y2, we will also got the similar image. Plot y2. Okay. Yes, we close it. So here we can define a new variable called t. T we use line space here. So basically, the line space we will need to input three values here. The first one and the second one is the starting point and the ending point of your interval, and the last number is how many steps you want to go through the interval. And then we can plot. We can plot t to y. You can see the screen here. And what if, so now we have some solid plots, but they only appear in a figure window, and then they disappear as soon as we plot something else. And never fear to make a plot that stick around when we plot something else. Just use a hold command. For example, I use plot ty also, plot ty, and I with this image, I use hold on command. So now if we put something else, we plot something else, like I plot t y2. We see the graph again. Can you see the graph, right? You can see the graph. Here, both t versus y and t versus y2 appear on the image. Here, we can also use a hold off to descend our control. And if we plot ty again, we can see there's only one line here. And this image is somehow nice, but we can make it look nicer. So let's add a title and some axis label and a legend there. to make our plot meaningful. So I can use title. I want to call it my plot. See? You can see the image is my plot here. And I want my X label is equals to time. Yes. It appears. And also the Y label, I want it to be amplitude. So with these labels, I make my graph look nicer. And also, if we want to change the style of the graph, we can use plot like T versus Y with the star notation here, and we can also control V with some more lines. Yes, we can see here, and I can use the O2 instead of star. We can see some dot here, and I can also change the size of my. I can set my line width to 3. My marker size equals 3, and I make my graph to red. This R is implies my plot will be red. Okay, here it is. So for more line and marker options, as well as other information regarding plotting, you can consult the help menu, right-hand corner of the screen here. You can always search the documentation here. You can see here's a lot of plots functions. Okay, and next, let's say something about extracting data points from an image. You often come across the charts in an image form from which you need to extract data points either for data-driven modeling, for comparative study. And now to do this, you need to use one of the file package called Grabit. We go to the home, click the add-on. It will open the add-on Explorer. Okay, can you see? Let me share. Can you see the add-on Explorer? Okay, and we can search Grabit. Grabit. And you can click here and install it. I have installed it, so I just need to open the folder. Okay, so in the folder, we will see some data here. Here's a script file. We can double click it to open. And we can run it to see what will happen. It will open interface. Can you see the interface? Okay, let me share my screen. Can you see the interface here for the Grabit? Okay, thank you. And in this page, we can do our data points extraction. We need to open the folder, run it, and for example, this is an image file. I can first click the load image, and I will find from my desktop here. Here is just an image. I download it from Google randomly. It shows a stress strain curve of steel and aluminum, and now from here you need to extract data points so then we can do some further analysis. Okay. we have successfully loaded the image, and now we need to calibrate it. We click this button here and follow the instructions. First, we need to click on the origin axis, the origin, and we enter the value, which is 0. Then we need to click the maximum value of axis, which is 0.175. We do the same thing for the y-axis. 0. And then 1, 2, 0. Okay, we have labeled our axis and y-axis, and then we can create grab points. We can first extract the aluminum data. We just click along the graph. You can see our preview box here is the data we have selected. And we continue to click. Okay, I have clicked more than 20 data points. I think it's fine. So I click it again. Yes, it will save as an 23 times 2 array into this data in memory. We do the same thing for the still graph. Click grab points. From here, we can do some data extraction. We can see the preview box. Okay. Click again. It will create 2 sets of data, and the first one is alumni. To distinguish them, we can rename it. The first one as data AL. Yes. And the second one, we can call it data ST. So after doing this, our data will be saved to our workspace, and then we can use it for our later analysis. And let's wait for it. Okay. And you can later use this graph to plot your data points extracted. Okay, we need to wait for it. It will start. Never mind. Let's just wait for it and wait. I will give you some introduction to our last 2 examples. We come back to Google Doc. Can you see my screen? Okay. So next to deploy what we have learned before, and let's see some examples. The first one is a random theory, which is also the random walk. The random walk theory suggests that the changes in the model have the same distribution and are independent of each other. Like for example, the price of stocks can be viewed as random walk model. Here we can say from the definition in Wikipedia, it says in the mathematics, the random walk is actually is a mathematical object, and it describes a path that you can either go any directions before you make your next step decision. And to make use of random walk, we can write some codes in our MATLAB also. It seems that my MATLAB is stucking. I will reopen it, so give me 5 minutes. Hope you can see it now. To make a random walk with MATLAB, we can open a new script. And I will do the coding here. So we use random walk in 2D. Before we do anything, we can close all and clear all. Clear what variables we have made. And I define the number of steps to be 10. And x1, I let it start from 0.0, and y also, y1 start from 0.0. Here we can make use of our for loop. So for I equals to 1 to number of steps and steps. Okay. We can define a theta here, which is theta equals to 2 pi times random. Theta is actually the angle between 0 to 2 pi, and the random function will return some random value between 0 to 1. So the whole theta's range is from 0 to 2 pi. And we let each step to be the unit step r equals to 1. Later we can modify it. For each of step, we have found the value of r and value of theta, and then we need to do the step size. The step size on the x and y axis, we can easily call them dx and dy. It's very easy to derive them. The ds would equal to I times cosine theta. And dy should be r times sin theta. Yes. So basically, they are the changes in the respective axes. And x, the position of x, we use xy plus 1 equals to xi plus dx. Similarly for y. Okay, we use y I plus 1 equals to yi plus dy. Okay. And here we can plot the function x, y, and I want z to be right value. Can save it as I say it to my document, MATLAB, save as random walk, done walk 2D. Okay. We can run it to say, oh yes, it gives me a figure. Can you see the figure? Okay, the points is very limited because we only have 10 points. Now let's increase the number of points to 100. Okay, let's run again. Okay, it seems nice. It seems nicer now. And next, we can increase the number of random steps. And now we want to combine that with some arbitrarily chosen step size. So let's add a new variable, the lambda, to be the mean free path. We add lambda here. It's the mean number of free paths. And we set the number of steps to be 100. So how it will be used? It will be used to modify the R. Here, the R is going to be 1, but we need to modify it to be minus lambda times log random. Okay, so here R it will be a positive value. And let's run it to say. Okay. You can say the graph looks a little bit nicer. And then to do a 3D version, instead of having R and a theta, we are going to add another 2 more variables, the z-axis, and also the angle implies the vertical movement. Conventionally, the theta is defined equivalent to the latitude, and the theta should be in a range from 0 to pi, and we define a new variable called phi should be from 0 to 2 pi. And in this case, we can define a new variable z here. We also let z come from original point. And for the theta, we let it to be pi times random because we know that the theta's range is from 0 to pi. And later the phi, we let it to be 2 times pi times random. And R, we remain it as minus lambda times top log random. And here we can add dz. So dx here would not be r times cosine theta at all. It will be the projection on the x-axis. So it will be sin theta times cosine phi. Right. Sin theta times cosine phi. It will be the projection on x-axis, cosine phi. And respectively, this dy should be sin theta times sin phi. And dz should be r times cosine theta. It will be the projection on z-axis. Yes. And we make z I plus 1 equals to AI plus DZ. Okay, so we make our output to be dot form, and we run it. Okay. Oh no, I forgot to edit this. We need to put 3 variables. Let's do it again. Okay, it seems I have an error here. Oh yes, I forgot to add the variable, new variable here. Okay, let's see. Oh, it generates some very nice, okay, I share my screen. It generates a very nice graph here, but the number of points should be a little bit small and we cannot see very clearly. Let's increase the number of steps to 1,000 and see what will happen. Yes, for now it seems a little bit nicer. Okay, let me share my screen. For now, it looks a little bit nicer because we can see a bunch of different points, but it will also be very, very difficult for our humans to view it as such a different range of axis and y-axis. So to get the better view, we are trying to put all the points onto a sphere, which is we are going to reach the isotropic distribution in 3D. So we close all. What we will need to change is we don't need to modify the R at all, and we can make it as a unit step as origin. We also don't need to do the changes because we don't need to move. We just need to see the positions of our points. So we don't need our DI and something. We also don't need the movement. We can delete them and do SI directly equals to R times sin theta times cosine phi, which is a projection on axis and y-axis, also z axis. And let's see what will happen here. Here it goes. Can you see the image? It forms a very nice sphere. Maybe some of you, maybe many of you say it will be a telescope, and we can make it. We can spin it. Yeah, because of axis, sometimes it will show as a telescope. To make it more dense, we can add the number of steps to be 5,000. Okay, let's run again. Okay, here it is. From the points are actually not uniformly distributed. We can also view it from the graph. And as you can see, the points are clustered more close to the poles than they are towards the equator. The density of the poles is much more dense than the equators here, which means if we randomly choose a direction, and there will be a bias towards the north and south poles. And this occurring because while the value of phi we are generating is uniform, the theta we are generating results in a cluster of points. So it's very easy to imagine that actually we are generating almost the same points from each latitude. And near the points, the density of our longitude is higher. So the number of points is also increasing. But how can we achieve the uniformly distributed points? We must adjust the density appropriately. So how to do that? You can think about it, and I leave it to you as an exercise. Okay, next we are going to talk about another very interesting example called the Monte Carlo simulation. Let me share my screen. Okay, this is a isotropic distribution in 3D. So what is Monte Carlo prediction? Always say Monte Carlo simulation. Wikipedia says it's repeated random sampling to obtain the numerical results. And from mathworks.com, it's even a bit more specific, saying, he says Monte Carlo simulation is a process of generating independent and random draws from a specific probabilistic model. Actually, it's the Monte Carlo simulation is a computational algorithms that rely on the repeated sampling to obtain some numeric results. And the underlying concept is to use randomness to solve problems that might be deterministic in principle. And this is the most greatest thing about Monte Carlo simulation. It uses uncertainties to predict the certain things. So why and where are Monte Carlo simulation used? It can help us to answer the probability questions, like in the finance for economic forecasting. We can use it to do the risk management and some other things. In automotive, it can do the sensitivity analysis. And in the weather, we can use it to do the weather forecasting. Here we know what and where Monte Carlo simulation can be used. But how can we, as students, as learners, to make the Monte Carlo simulation? We can just summarize it as 3 simple steps. The first is to start with a simulation model. And the second step is we run that model many times with some randomly changing parameters. And the last step is we analyze the results we got from the previous 2 steps. Today, we are going to use a very interesting game, which is a casino game, classical casino game called Blackjack. I believe most of you have heard of this game, and I will briefly tell you the rules of it. The rule is to, the general object is to get your hand with a value very close as much to, but not more than 21. So you can draw a cards, and all the face cards are worth 10 points. The ace cards are worth either 1 or 11, and all other cards are worth their numerical value. You can say the figure here. This is you. This is a dealer. You are playing against a dealer. You each starts with 2 cards, and your card is face down, but one of your dealer's cards still face down. You can make 3 actions to respond to this situation. The first one is double. You can take 1 more card, increase the initial bet by 100, which means double your bet. And the second action you can do is to stand. You take no more cards and say what and review what is the dealer's remaining card. And the third action you can do is called hate. You can take 1 more card. So this is generally the rules for Blackjack. And we'll say here MATLAB app. Let me share my screen. We will see, we go to the home and click the add-on. We can search for Monte Carlo. We can search for Blackjack. Blackjack. Here it is. You can download it. I have pre-downloaded, so I just need to open the folder. Here it is. We can see some codes that are pre-created by the documentation creator, and we can try to run it. It will also give us an interface, just as a slide shows. So we need to play with the dealer, which is also our computer, to win more money. And here, okay. It is still processing. Okay. Can you see? Oh, I think cannot. Okay, this has an error here. Need to go to fix it. Okay, seems it has some error, but it will be okay if we just use a 0.8. So from the Monte Carlo simulation, you can try it on your own computer. To play with it, it actually has some we call the strategy. So if the basic strategy is if you got in total 17, you never stand it. And we can also create a new script file right into the same folder with the Blackjack game. And this one, I will show the codes here. Okay. Let me see. Okay. I create a new doc here. Instead of playing with Monte Carlo manually again and again, we can actually write a new script file. We write a MATLAB code to make our machine to do it for me. So here is a code I have write it before. We can see. So first is a parallel pool local 2. This one is to distribute what's your processor in your computer processor to because we need to do the repeat work, and this will be a very large work. And then I assign a new member called P, which is the number of players. I assign 15 players to play the games against computer for me. And each of them will play 2,050 hands. And in the B, I create an array called B with all zeros. Here is B with all zeros, N and P. The rows index are N, and the columns, their index are P. And here we can see the parallel for. We use a parallel for loop to make it run, and we can say we use it to play against a computer. And later we can plot some figure on it. I have already plotted it. Let me show. Okay, I think after this workshop, I will show you the figure. And but here is basically what we are doing to find the relationships against the behind the Monte Carlo simulation with a Blackjack demo. And I can told you that in the long run, the casino still has a 0.5% higher probability of winning. So that will be very interesting. And later I'll show you the graph of it. For now, it's already 8. Let's take 10 minutes break. And after this break, Stanley will brief you more about the deep learning toolbox and the detector later.
Hi everyone. Could you download the computer vision and automated driving toolboxes before we begin? So the break will commence now. We'll see you back at 8:13. Okay, hello. I don't waste any more time. So we just do this. Okay, so I'll begin with an overview of deep learning because some of y'all may not know what deep learning is. And for MATLAB, I would like to use computer vision as the main form of sort of deep learning, machine learning. So for computer vision, the overview would be the first part will be doing separation. You want to extract the features of, say, of an image. You want to find what stands out in an image. So in that case, sometimes we use the tools used generally are blob analysis, which is finding the shape of the object, or color thresholding, which is separating the features based on what color they are, like red, blue, and green. And there's also feature-based object detection, which is using these two feature extraction methods. One will be the histogram of oriented gradients, which selects the correct details of each image and pushes it out. And so you can identify what kind of shape it is. And there's also the sped up robust features, which will also do similar sorts of things. For machine learning, there are two main methods for computer vision. One will be support vector machines, which would define a boundary between what's your points of interest. So when I classify, say, A versus B, I would generally use support vector machines, and I'll find a distance, what's the optimal boundary that separates, which classifies each data point into each output. For the Valor-Jones algorithm, it's also mainly used for image detection, but it's a bit complicated, and I'll put the link inside this PDF file and you can refer to it yourself. For deep learning and for computer vision, people generally use convolutional neural networks. One will be the RCNN, which is it's also very similar to CNN, and the other one is YOLO, which is you only look once. So instead of going through this entire process of CNN, it does two things at the same time. So you'll do bounding boxes, and you also do a probability matrix, and you'll combine it to give you the result. So for using MATLAB, for deep learning in MATLAB, we rely on something known as ground truth, which is something you define as the real and empirical data that the algorithms and neural networks can use to identify and continue to interpolate. So something will be, the ground truth will be something like labels on a video, which is what you see over here. this is something I define, and the machine will continue to use, the programs will use it to continue to give us more data. So let's jump into the notebooks. Okay, so to begin, I want to start the demo. I'll start it in, this is a live script as you've seen just now. So to start this demo, I'll run the demo to clear anything I have inside my file. And I'll access the current folder, I'll access part 1. Then I'll begin the object detection. So first I'll go through is what you can do with MATLAB. And once you can define variables to call these functions, which is video reader, I'll just show, I think it's easier to understand. Oh, hold on. Let me just change my share. Share my screen instead. Sorry.
Okay, while we are waiting for Stanley, and I want to give you some instructions for the Blackjack form. Stanley, you can try to share your screen, and I will pick up the Blackjack. Okay. And I think I'll share my screen. Can you see the card playing? So here I got a 2 and a K. So I want to double it. I click here. Oh no, I lose $20. So I deal again. 19. Definitely I will stand it. Yes. The dealers, its number sum is going to exceed 21, so he lose. We just do this randomly, playing against dealer. So this one I can use double. Oh no, I lose. So let's just stop it. Instead of doing it manually again and again, yeah, we can definitely let the machine to do this for me. And let's follow a more systematic Monte Carlo-like approach. So the rule 2 just now says run the simulation many times and let's exactly do that. Okay, I will show the codes I have showed you before here. We can use Monte Carlo. Okay, I just paste the codes here. Here is, and I save it as Blackjack. Blackjack, Monte Carlo. Save. Okay, if we run it, we will use, because our computer is multi-processor, so I want to use many processors of my computer. So here I distribute my different processors to do different works. Yes, and the parallel 4. This is parallel 4. Yes. Now it seems nice. Okay, it was executing. Can just wait. Stanley, have you ready to share your?
I can share it.
Okay, after it has successfully executed, I will show you the graph. Okay, thank you.
Are you able to see my screen now? Or is it still a black screen? Okay. Okay. Okay, so first, right, I'll begin by starting a demo. I think y'all can see, I'm not sure if y'all have any extra stuff in your workspace. And workspace is where, I'm not sure if you mentioned before, but it's where all your variables are stored. So what you should do is you should clear everything. CLC is you clear the command window, and clear is you clear all the variables here. So what I'll do is I'll run to clean everything up. So first, I will go through this thing, which is playing a simple video on MATLAB, which is something you can do using the video reader app. And you can call the file name. It has to be in the same folder as what you do. So you have to change your current folder in MATLAB. You can't just, if you run it in a different folder, you will not find the file and you'll face an error. So what you should do is always change your current folder to what you want to use. And I'll run the section. And as you can see, okay, so yeah, you can see that there's a deploy. As you can see, there's a deployable video player, but okay, that's not important. So the labeler that I will use is something called the video labeler app, which I'll run this section, and you can see that it opens up this app, but it take a while because it loads a little. So what this video labeler app does is you can select labels for each object inside the video. Okay, so what I'll do next is I'll import a video, I'll add video, and I'll choose this bio run to GT. And it'll take a while to load the video. Not sure if it's loading. Okay, there we go. As you can see, right, there's this video here. Okay, this is a bit blocking my okay, I'll just put it somewhere here. So what you can do is with this video labeler, I can click label. I want to label this red buoy over here. So I call it big red buoy. And I can define the color. Since it's red, I'll choose red. And okay. So once I have that, I can actually define, okay, you can see that I can draw this label over here. Let me just move this. And this is my label. So the thing I want to do next is, okay, so I need an algorithm to help me track this thing. Because I don't want to keep doing this every single frame because it will get tiring. Like if this video was any longer, I'll be doing upwards of 100 frames each. So I'll just have to I'll select the point tracker algorithm and I'll click automate. Okay, this will take a while. Everything's laggy with my lab. All right, so as you can see, there's this label for the item already. And also you can create sub-labels for this big red buoy, but of course I'll do it later. And you can just run the video. The point tracker algorithm is very simple. You can just select your item and let it run. It'll just run by itself. And okay, it figures out that, okay, this item is over here and I'll continue focusing on that set of pixels. So once I'm done, I'm happy with the result, I click accept. And as you can see, this is the finished product that you'll continue tracking that one, no problem. Okay, good. So now I want to focus on a different kind of algorithm. I see this green buoy over here, and at certain frames, at a certain point of the video, it'll go out of frame, which I don't really want it to do that. So what I'll do is I'll also define another label. And I'll select the color, maybe I'll put it as green. Big green buoy, very nice. So what I'll do now is I'll select the temporal interpolator, which would I will have to select a bunch of frames for it, and it will interpolate where this thing will go. It's not perfect, but it can do the job pretty well. So what I'll do next is I'll run the video and let it run for a while. Okay, this is where I want to interpolate it. And maybe I'll skip a few frames forward because it's interpolated, it will continue tracking this thing. So even if it goes out of frame, it will try to guess where it is. Actually, this doesn't go out of frame. Okay, but as you can see, it zooms in a bit. So this actually moves. So every frame, I will continue to shift it. And maybe towards the end, it goes out of frame, and I'll just select a bit only. Okay, then it's no longer there. So what I'll do now is I'll run the entire thing. Go. So you can see that it's not perfect. You'll try to track this thing as it goes away. And I'm happy with it. I'll select accept. And you want to see the entire process. Maybe since I start from the very beginning, and since there's no label, it doesn't actually identify anything yet. But once I start, when the label starts, it will start identifying, oh, this is the big green buoy. And if I'm not happy, if I don't like that it's a bit too big over here, I can adjust it and it will continue accepting it as the correct thing. Maybe I should widen it. Yeah, and you'll follow that. So additional features. So this is very basic labeling, and you can actually do more labels at the. So there are sub labels you can include inside. Like let's say I want to say center. I can draw the center inside here. Okay, I want to draw the center and I'll say okay. Or maybe I can okay, a lot of problems with this. Okay, I think I'm lagging a bit with MATLAB. Okay, never mind. That's not the important part because most people don't really care. Okay, so afterwards, when I'm done labeling all the things that I want to label, I want to save this session. I can save it and I can actually put it under a mat file. Or if I can export it to my workspace. As you've seen before, there was the workspace and you can call it the ground truth, which is what I'll call it, but I'll call it ground truth 2 because I have another file saved inside there already. And I'll close this thing once I'm done. Okay, next. So now we have this ground truth labeler where I'll show you this one. Okay. Well, I'll just run this section. I'll show you. Now I'll be using something known as a ground truth labeler, which could be found in your automated driving toolbox. Now this is very similar to the video labeler, but it's optimized to run on that file. And this is the finished product for the labels. It looks quite nice. Okay, I need to shift this around. Okay, so as you can see, all the labels are very nicely labeled already. And you can see all the labels moving very nicely with where the thing goes. Okay, so once all of this is done, you can move on to you can save this ground truth as this mat file over here, where we use it as our data set, our label set. And then we move on to using this thing known as, we're going to train a detector to detect all of these labels. So first I'll load the data and I'll use the ground truth labeling.mat. Should already be here. And as you can see, the ground truth 2 is over here, and there's also the ground truth over here. And I'll select the labels that I want. I only want big red buoy, as you saw just now. I'll run that. And what this thing does is I'll create this file called the training data, where you will import all of the label data sets and you will basically fill it up. And I'll take a sampling factor of 2. So because this is a video, I'll take a lot of images instead, because videos are just frames by frame and there's a lot of frames added together and I can't get exactly every single frame. So I'll choose a factor of 2. And so I have 107 images there. And now I'll train my detector. I previously trained it already, so this will take a while. And I choose particularly this ACF, which is called the aggregate channel features, which will capture the features of the object of the image. And it's actually a MATLAB algorithm that is, you can call it, and it will train itself, and you will use the training data as mentioned inside this folder. And you do have to remember to add a path to it. If not, MATLAB won't recognize it. And I choose the number of stages. I choose 5. So you can see we are still at stage 3, and we're finding you can read through all of these, but generally you can choose the number of stages, but I chose 5 because I wanted it to be nice, but I don't want it to take too long. So after training this detector, you can save the detector itself, which is called over here detector. You can save it and under detector.mat, and you should also remove the path training data. Okay, now that it's done training already, it shows the completed. I will save this in my file. I'll run this section. Okay, and I saved it already. Okay, as you can see, it will appear in my folder detector.mat. And now I'll go on to showing how I will use it inside the actual video I'll run this section to clear all of my output, my variables, and my output over here. I'll use part 2 of this folder. And next, I'll load the detector. And at the same time, I'll load the video reader, so what it chooses to read. I also use this thing called the deployable video player inside MATLAB. And I'm not sure if Shulin went through this just now, but I'll create something known as a struct. I'll initialize this thing known as a struct. It's very similar to, in Python, you will call it like a data frame or dictionary. It's similar to that. And next, I will get the data, which is, I'll read the frame of the video reader, which is the video itself, and you'll go frame by frame. And for the bounding boxes and scores, I'll use the detector to detect it. And afterwards, I will get the variables for the scores, and I want to choose the best scores for each of them, and I'll print it inside the video itself. So there's something known as insert object annotation, which will annotate the labels itself, and I'll just run it so you can see it. As you can see, there's the confidence level changing. It's not exactly the most robust tool because you wouldn't use MATLAB for this kind of things, but it's definitely a good way for you to annotate. So you could run Python along with MATLAB, and this could be your way of visualizing your data. And if you are curious about the results, if you want to see the results, I can delete this and show you the results again. Okay, I have to delete the. Actually, I'll show this later. Okay, once I'm done, I want to release the video player. I don't need it to continue. And now we'll move on to how we can evaluate the object. So what I'll do now is I'll load this ground truth evaluation, which is the data set to test the data. So instead of the training data set, I'll use the test data set right now. So I'll run this section and it should appear inside my workspace. And I want to continue looking at my red boy. So I will select the labels and run that as well. And I'll add the path to my evaluation data, which is the same. So you'll pull the evaluation data and you will make a variable out of it. And it will sample or sampling factor 1. And you'll write to the file known as evaluation data. So I'll run that. And this one will store all my images. And this will initialize the boxes and scores. Okay, as you can see, it was added already. Now I'll process the data. And I'll run this section. So this collects all the scores in the detector. And now I evaluate the detector to see whether it works. So this is basically training the data set. Training the detector with the data set. And now I evaluate the detector. So I'll choose with this is I can show you the readings, but there's not much point because I can run this section. Okay, I can show you what this actually outputs. Because it will output sort of like, it's very similar to a data frame and you really wouldn't be able to see what exactly this thing is saying. It's almost done. Yeah, you can see that these are the scores available, but there's so many of it and it doesn't show the whole thing. So there's not much point to it. So I would rather just use our graph to plot the entire thing out. You can see that there's a lot of confidence level scores and it's not very good. I can't really understand it. So instead I'll use our plot to do it. And I'll run this section. And so what this does is it looks at all the precision and I'm using this function called the evaluate detection precision. So it'll grab the results from over here and it will, it'll print out a graph for me. So I'll use, well, if you're familiar with Matplotlib, this should be no problem. Subplot, I'll plot one each side. So you can see that the precision actually improves overall, and you can see that the miss rate continues to drop. So that's the whole idea of the detector improving itself. Okay, then afterwards, after I'm done with the entire thing, I'll remove the path for the evaluation data, and that should be my detector. Okay, so that's all for my part. And as you can see that MATLAB isn't the best tool for deep learning, but it can be very effective because it can show you all of these visualizations and you can see how it works with, say, video data, whereas for Python, you won't really be able to visualize video data. So it can work hand in hand together to help you effectively do your deep learning projects. That's all. Thank you.
Okay, all right. And here our model has draws a conclusion and I can share you the results of it. Can you see the graph, plotted graph? Okay. So there is in total 15 lines here, and each line is represents one player. And here is the total money return after they play 2050 hands with computer. We can see there actually are some people that are winning money, but there are also some people they don't win and don't win much and don't lose much, and some of them lose most of their money. And so to do the calculation, we can add all their earnings and losses, and we can say their total return is equal to minus 2050 of 585. And we can say in the long run, the casino still takes the advantage, and it still has a 0.5% higher probability of winning. So this example is actually a very interesting example to let us get more familiar with the Monte Carlo simulation, and all the pictures and all the techniques you can also find in the mathworks.com. And here's all the contents from our workshop. And before you leave, I want to get your feedback. Let me share my screen. Okay. Will you please fill in the feedback form, and later I will send all the codes and documents for this workshop to all of you. Thank you.